Hi, what's that? Oh, you'd like to learn about computing and analysis of variance by hand. Yeah, we can do that. At least we can do most of that. In this video, I am going to talk about the purpose of one-way analysis of variance, when we use it, what it's for, and I'm going to teach you how to get what we call the omnibus result, the overall result. In this video, I'm not going to talk about computing effect size or doing post hoc tests, just because it's still going to be a long video with just limiting myself to the overall, what we call the F statistic or F ratio. That probably doesn't make any sense yet if you know nothing about analysis of variance or ANOVA, but let's get started. If you are one of my students or you've been watching my previous videos, you may already know about t-tests for hypothesis testing. Analysis of variance is kind of like an extension of the t-test, and it's got some similarities with t-tests. The one I'm going to be talking about in this video, because there are different types of analyses of variance or ANOVA. We have, in my class, we learn about one-way analysis of variance, repeated measures, ANOVA, and then we learn a little bit about something called factorial analysis of variance. There's also something called analysis of covariance, or ANOVA, which we don't cover in my undergraduate class, but my grad students get to learn about. I know you're like, hey, I want to go to grad school so I can learn all about that. But let's talk about probably the simplest one, your one-way ANOVA. What does that mean? Is it similar to a t-test? It's actually it's similar to the independent measures t-test or independent samples t-tests, which, if you remember from learning about it previously, that's where you have two groups to compare, two independent groups, and you want to compare their means. A one-way ANOVA can be used for that situation too, but you can also use a one-way ANOVA for a situation where you have one independent variable and you have two or more groups. So you could have three groups. They still have to be independent. Just to give you a refresher, the assumptions of independent samples t-test and the one-way analysis of variance, the assumptions are, for the main core assumptions, first of all, the observations are independent. It's separate participants or subjects, different animals, different people. Their scores are not influenced by each other in any way. And another assumption is that you have the assumption of normality, that the populations that you're drawing those samples from, they have a normal distribution. And we have this thing called homogeneity of variance, that the variance across the groups or within the groups is similar. Now, variance is going to be very important for analysis of variance. You might have noticed it's in the name. So with a t-test, we were focused on comparing the means. With ANOVA, we are going to be comparing variance. What do you mean? What do you mean comparing variance? All right. We're going to get fancy with ANOVA, and we're going to take our overall variance. Previously, we just had one variance, like with an independent samples t-test. I taught about computing a pooled variance, one variance for the whole study. Now, with your ANOVA, you're going to have total variance, and then we're going to do this really cool thing. I know my excitement may not match yours. It's okay, but for me, I think it's cool that in ANOVA, we partition the variance. One time I made some stickers for my students for their final exam, and one of them, it said, I partition variance for fun. A few of them got it. Others were just like, am I done with my final? So yeah, I like statistics, but I know I am not representative of all people who study psychology. So partitioning the variance means we take our total variance and then we split it up. We partition it into two types of variance. And later with other types of ANOVA, we're going to partition it even further. But right now we're just partitioning it into two sources of variance. So you're going to have between and within variance. What the heck is the purpose of that? Well, with an ANOVA, we have to compute our test statistic. With a t-test, our test statistic was the t statistic. With an ANOVA, we don't get a t, we get an F. It's uppercase, capital F, italicized if you're typing it in APA format. The F statistic is the F ratio. It is a ratio. It's a ratio, a fraction, where the numerator is your between groups variance, and your denominator, your bottom number, that is your within groups variance. Why would we do that? Why does it make sense to do it that way? Because when we divide our between groups variance over our within groups variance, we are going to see how much our independent variable, our effect, the thing we think has an effect, how much that contributes over and above the within subjects variance, or within groups variance, within groups. All right, so wait. So what is the within? What does the within have to do with? That has to do with individual differences, the stuff that's always going to be present in any study, in any experiment that we conduct. You can't eliminate the fact that, let's say you have human participants. Humans are complex and they have individual differences. They have different motivation and personality and IQ and waking up and fatigue, and they're coming to you in different states of being. You can't eliminate that. All right. So you're always going to have some variability. You're always going to have some variability just from people being different or animals being different if you're doing animal research. Okay. But why do we care about the top number? Why do we care about the between groups variance? If you have treated your participants exactly alike, you've standardized procedures, you do all the stuff you're supposed to do for good experimental research, if you have randomly assigned them, so that means that those individual differences have been spread out roughly equivalently across groups, any other variance that you're adding that's distinguishing your different groups, that should be from your independent variable. It should be from your effect. You want the differences, the variability, you want the variability that you see from your independent variable to be larger than what you see just from individual differences that are pre-existing. So the F ratio is a comparison. How much more variability do we get from our independent variable compared to what's just already there from individual differences? Okay, so how do we do it? How do we get that F ratio? It's not a short process when you're doing it by hand. We have to do some preliminary stuff first. And when I show this to my students, they very often are like, that's a lot. It actually starts off feeling like a lot of work, but then you get towards the end of the process, it gets quicker and quicker and quicker. So you got to trust the process. Please trust the process. At the very least, just remember, like for my students, you have to know this to pass the final exam. So let's get to it. Let's find out what we have to do to get that F ratio for a one-way analysis of variance. By the way, why do we call it one-way analysis of variance? That has to do with the fact that there is one independent variable. You can do ANOVA with more than one independent variable. One way means one. All right. So a one-way analysis of variance has one independent variable. A two-way has two. Three-way has three. All right. And you might also see terminology where it talks about factors and levels with ANOVA. The factor is your independent variable, your grouping variable. All right. So like if you're doing a drug study, if you're comparing placebo to low dose to high dose, dosage would be your factor, your grouping variable. And each grouping variable, each factor, each independent variable or quasi-independent variable, if you're doing a quasi-experimental study, is going to have levels. Levels is simply the number of groups. All right. So if you've got 3 groups, you have 3 levels. 4 groups, you have 4 levels. So if you see that terminology, that's what those things mean. All right. Preliminary calculation time. You might notice I've got my whiteboard ready. We're actually going to need 2 whiteboards for this one. You'll see why eventually. Let me get started. All right. I've turned the light on. So now I'm blinking because I'm blinded by it. And so, by the way, there are going to be a lot of times in this video where you may need to pause or zoom in. I'm doing my best to make it all fit in and work, but here is our data set. And so here we have 3 groups, and they're the participants are randomly assigned to either do no studying, no practice, do 10 practice problems, or do 50 practice problems. And then the dependent variable, they're going to be given a test on the statistics that were in the practice problems. And so they're randomly assigned. So it's, my video just went blurry I don't know why I did that. They are randomly assigned to each one of these groups, so that makes them independent. And there's only 3 participants in each group, which in the real world, that's way too small, but I want to reduce our computations as much as possible, so that's why there's only 3. In the real world, you're going to see more than that. All right, then this is made up data. This is fake. All right, so what do you have to do first? Once you have your data in front of you, you have to compute preliminary stuff. And why am I putting this on a separate little whiteboard? It's because to leave room on here for other computations that we are going to have to do. So what do you need to compute? These are your preliminaries. They're going to be needed to plug into various formulas. So first of all right, we have the N. The capital N is the number of scores, the total number of scores in the whole study. So it's 9, and you can verify that. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. We got it, right? We got it. Okay, so that's capital N. Let's hold it this way. Capital N. Got some glare. All right. Capital N is 9. All right, we know how to do that one. You also need to compute this thing called G and GM, but actually it's easier to compute those if you compute the other things first. So first of all, you have to compute the lowercase n for each group. Lowercase n is the number of scores in each group. And so I've labeled my groups 1, 2, and 3 on here just because that works for me. You can use any system you want for keeping them straight. And so N1, which is going to be our none group, I'm going to call that 1. All right, so N, they're all 3, but sometimes that's not the case. So you have to put the lowercase n. I apologize for the glare. All right, N1, N2, and N3 all equal 3 because each group has 3 participants or 3 scores in it. Then you have this thing called capital T. Capital T stands for total. All right. How do you think you compute that? If you're guessing that you just total the scores in a group, you're correct. It's a sum. All right. So the capital T, T1 equals, what was it? 3. 3, because 1 plus 0 plus 2 equals 3. T2 is 8, and T3 is 14. It's backwards on my screen as I'm recording. Get it out of the glare there. Now, the next part, I know you know how to compute this if you've done any statistics whatsoever, but the next part is to compute mean. Now, mean is actually easy if you've already got your N and your T in front of you. You just take your T and divide by lowercase n. So the first one, we take 3 divided by 3, we get 1. The second one, we get 8 divided by 3, we get 2.67. Now, I rounded to 2 decimal places, and that's how we do it in my class. If you are coming to this video from some other setting, I can't guarantee you that you will be allowed to round or that the person that you're presenting your work to is going to expect you to use 2 decimal places. That's how we do it in my class for consistency and simplicity. So how do we get this G? G is your grand total. So you can just take that by adding up all of your T's, all your capital T's, or you can take the individual scores and add them together. Grand mean is your overall mean. So you take that by taking the G. I shouldn't use this as a pointer because it's supposed to go by my mouth. Take the G, the capital G divided by the N gives you the grand mean. All right, why do we need all this? We're going to plug them into some formulas. All right, so I've left space on the board for the many formulas because eventually we are going to have to fill in something called an ANOVA summary table. You might be thinking, wait, aren't we just supposed to be getting an F ratio? Not getting an F in the class. No, we're not going to do that. Aren't we just supposed to be working towards an F ratio? Well, you need a table. to get to your F ratio. Let's set it up first. All right, so we've got our table set up here. Every time you do an ANOVA by hand, you should be setting up your ANOVA summary table. For a one-way ANOVA, it looks like this. And you might notice that some cells are missing. That there's a reason for that. You don't put anything there, but we are going to be putting numbers in each one of these cells, and some of them are much easier to compute than others. One of the easiest cells to fill in is this thing called DF. You may remember from previous stuff that that stands for degrees of freedom. Typically, the hardest one to fill in, 3 of them, are the ones with SS. If you've learned about t-tests and other things like variance, you may remember sum of squares as being what SS stands for, specifically sum of squared deviation scores. We still have that, but it's partitioned into different sources. And then you have mean squares, which is actually very easy once you've done the other stuff, and the F statistic, which is very easy once you've computed everything else. So what are these sources? What are the sources of variance? All right, so our sources between, within, and total, because remember, we partitioned. Our source of variance has been partitioned into between, within, and total. So now we can fill these in. Let's start with our degrees of freedom. I just realized as I was getting ready to fill this in that we forgot one of our preliminary numbers, K, lowercase k. What does that stand for? It's just the number of groups. All right, so when you see K in a formula, number of groups, in this case, 3. And I'm hoping you can see my colored dry erase markers up here. But so for our degrees of freedom, how do we compute those? So degrees of freedom between, your degrees of freedom between, that is K minus 1. So our K was 3 because we have 3 groups. 3 minus 1 equals 2. What do we need this degrees of freedom for? When we report our F statistic, we are actually going to need to report the between and within degrees of freedom. So these are going to be important not just for computing other parts, but for reporting your actual F statistic result. All right, now within. Within is K times n minus 1. N minus 1 in parentheses, lowercase n. So the number within each group. All right, so we have 3 within a group. So 3 minus 1 is 2. K is 3. So 3 times 2 equals 6. All right, and then how do we get degrees of freedom total? You just add them up. 2 plus 6. And so you get 8 for your degrees of freedom total. All right. Now we need to fill in the sum of squares cells, and those are the ones that take the longest and get students ready to give up because they're like, is it all going to take this long? No. If you can get through this, you can get through anything, and we're going to get through it. Let me show you how. All right. So I have filled in part of the table here, and I've got it color-coded. Let me turn the light on, so maybe it'll help you see it. And blind me. Oh my gosh, I can't see. I don't know if that helps much. Let me see. I feel like you can see it better like that. All right. You may need to, again, pause, zoom in. So what did we do here? So this is the formula to get sum of squares between. I put the little b next to it to indicate that we're computing sum of squares between for this one. And so for this one, it's the sum of t squared over lowercase n minus capital G squared over uppercase n. Now remember, we computed the t's and the g's and the n's in our preliminaries. All right, so how do we do this? All right, so sum, this sigma symbol means sum. So we are just going to add up, but what are we adding up? So t squared over n. So for each group, we get a t squared over n. So you have to square the t and divide by n, which is 3 for each group. All right. And so here you can see where I've done that, and I made sure to put the parentheses around that. Remember PEMDAS, order of operations. That's to remind you, you have to do this first before you deal with the g squared over n. Again, for some students, this is a point where they have to kind of pause and take in what I've done for each step. No shame if you have to do that. If you feel like I'm going too slow and you did really well in, your math classes and you're like, I know how to do this, you can play me at, double speed or something, all right? It depends on the student, how fast you need me to go and how many steps you need me to show, all right? But no shame if you need me to show you every single step, so here they are. All right, so for the first group, the t was 3. So it's 3 squared over 3 plus 8 squared over 3 because the t for group 2 was 8. The n for group 2 is 3. And then 14 squared over 3. And remember, where did I get those t's? We conducted those in the preliminary. Now, then we subtract g squared over n. G is 25. So 25 squared divided by 9, which is your capital N. And so we square these numbers, we get 9 divided by 3 plus 64 divided by 3 plus 196 divided by 3. Where do we get those numbers? We're just squaring our top numbers up here. And then 25 squared is 625. So we get 625 divided by 9, and then we go ahead and compute what those are. So it's going to be 3 plus 21.3 plus 65.33. Minus 69.44. Now we do have to compute what's in the parentheses first before we subtract 69.44, order of operation stuff. So we get 89.66. That's what was in the parentheses here. And now we subtract 69.44 from 89.66, and we get our final answer for sum of squares between, which is 20.22. So what do we do with that number? We take that number and we put it up in our ANOVA summary table. So we get sum of squares between is 20.22. We are now able to compute mean squares between. I know you're excited. I'm excited. Well, how do we do that? What's the formula for mean squares between? It's actually quite simple and straightforward. Sum of squares between divided by degrees of freedom between gives you your mean squares between. So we can fill in that cell. All right, so we've got our mean squares between. 20.22 divided by 2 is 10.11. Rounding to 2 decimal places here. All right, so now we've got one more cell filled in. What do we do next? We got to do this one. If you've ever computed sum of squares before, like for computing variance or for a t-test, you may remember the long process of computing deviation scores and then summing those deviation scores squared. That's what we do for this one. You have to compute a sum of squares, traditional sum of squares, for each group and then add them up. All right, it's a bit of a hassle. If you are getting to this point in a statistics class, you probably are familiar. You should be familiar with computing sum of squares by this point, and you got to do it for 3 groups and then add them all up. All right, so I'm going to get a little closer to the board here to show us how we're going to get those sum of squares that we're going to add up to get our sum of squares within. So for each group, I erased the none over here just to make more room here. All right, so for each group, we have to subtract the mean from each score. We compute the deviation score, which is the score minus the mean. And so the mean for group 1 was 1, so 1 minus 1 equals 0. See how we got all of these scores? And then the mean for group 2 was 2.67, so 3 minus 2.67 is 0.33. 2 minus 2.67 is negative 0.67. And then the mean for group 3 was 4.67, and so we subtract that from these scores, and that's how we get these deviation scores. The next step is to square each of these deviation scores, and then we're going to add them up. All right, to show you in pink is where I squared each number. So each of these pink numbers here is that deviation score squared. So like 0.33. It comes out, you square it, it comes out to like 0.1089 or something like that. I'm rounding to 2 decimal places for simplicity, so we round to 0.11. And so how do you get your sum of squares for each group? You just add up those squared deviation scores. So you add up 0 plus 1 plus 1. For the sum of squares for group 1, it's 2. You add up 0.11 plus 0.11 plus 0.45. The sum of squares for group 2 is 0.67. And just by coincidence, coincidence or, something going on in the study, the sum of squares for group 3 is also 0.67. Because remember, when you square negative numbers, they become positive. So you're always going to get positive sum of squares. All right. So what do we do with those now? To get sum of squares within, we add them all up together. So sum of squares 1 plus 2 plus 3. If you had 4 groups, you'd have to add in another sum of squares, all right? So it depends on how many groups you have, how many numbers you have to add up together. So you add up those numbers and you get 3.34, and then we put that in our table. So our sum of squares within is 3.34. Since we have now filled in the sum of squares within and the degrees of freedom within cells, we can now compute sum of squares total and our mean squares within. All right, so we've got more of our table filled in. So the way we got sum of squares total is we just added up sum of squares between with sum of squares within. We get 23.56 because 20.22 plus 3.34 equals 23.56. Now, your mean squares within is sum of squares within divided by degrees of freedom within. So it's going to be 3.34 divided by 6. So we get 0.56 as our mean squares within. Now we have all the ingredients to compute our F ratio. All right, so our formula for the F ratio is I got my finger in the way. Mean squares between over mean squares within. And so remember from up here, that's going to be 10.11 divided by 0.56, which gives us 18.05. So now we know our F ratio, that's our test statistic, 18.05. Well, is that a good one? Does that support a difference between these 3 groups? Well, just like with the t-test, we do need to determine if our test statistic, in this case the F ratio, is statistically significant. All right. One thing that's good to know about F ratios is if F equals 1, that means like no difference whatsoever. That means that the variance between equals the variance within, no effect of your independent variable. And this 1805, it's definitely bigger than 1. But is it big enough to be considered statistically significant? We are going to have to look up our F ratio in a critical values table, or we need to determine our F crit, our critical F value that we're looking for. So we're going to have to look that up in a table. All right, so there are various places you can get a critical F table. They're often in the back of statistics textbooks. This one is one that I got online. It's from a website by Statistics by Jim. And you have to be careful that you look at the F table for the correct alpha level. Typically in my class, we're using alpha level set to 0.05, meaning we only want a 5% or less, or we want a less than 5% risk of making a type 1 error. Here, you can see my little board in the back there. All right, so how do we look up our critical F? You can see how there are numbers on the top row and numbers down the vertical column. Those are based on degrees of freedom. And so on the top, we look for our degrees of freedom between. So remember, we had 2 for our degrees of freedom between. So I'm just going to have to point old school. 2. All right. And then we find our degrees of freedom within, which was a 6. We find that on this column here. So we see that 5.14. 5.14 is our critical F. All right. So our critical F, and we often abbreviate it this way, F with a little subscript that says crit. Our critical F is 5.14. Our F is 18.05. What does that mean? For your F to be statistically significant, it has to be higher than your critical F. So in this case, our critical F is lower than our actual F ratio, or you can say our F ratio exceeds the critical F. So that means we have a statistically significant F ratio. What does that mean? That means that we have detected at least one significant difference among the groups. That's what's known as an omnibus or overall result. We still don't know which groups are statistically significant from one another. All right, because it could be that all three groups are significantly different from one another. It could be just that the none group is significantly different than the ones who had any practice. We don't know. We have to do something called post hoc test to do that. But for this video, we are just focused on getting that F ratio. And so how would we write this? So in the box here, we'd write capital F and in parentheses 2, 6, y 2, 6. It's your between, your within degrees of freedom. So F with 2, 6 degrees of freedom equals 18.05, comma, P, lowercase p, is less than 0.05. What does that mean? We have a probability of less than 5% risk of making a type 1 error, or we have a low probability difference between the two types of variance. Basically, it is statistically significant, and so that means it's supportive of there being a difference among the groups. Again, we don't know which specific groups are different without post hoc testing, but we have detected that there is at least one difference among the groups. All right, folks. That's your one-way ANOVA, the basics of how to do it. Look at all that. Now, I'd show off our preliminary board too, but guess what, folks? I laid it down on the table and I sat on it. And apparently my butt in my jeans is a good eraser for that dry erase board. So, isn't that beautiful though? Look at all that. All that to get that. All right, folks. In the future, at some point, I hope to do a video also about repeated measures, ANOVA. This is what you get for now.